Hello everyone, welcome to my videos on elementary differential equation. This is video number 9 for chapter 6, and the topic for the chapter is systems of two linear differential equations. In this video, we consider the case where the A matrix has complex eigenvalues. Okay, so if now the A matrix has two complex eigenvalues and the matrix A has all real value entrants, then these two eigenvalues must form a pair of complex conjugate numbers. That is, we can write it out. Lambda 1 is alpha plus I beta. Alpha is the real part and beta is the imaginary part. And then lambda 2 will be the conjugate, which means you change the sign of the imaginary part and you get negative. Okay, so we can write the two eigenvalues in this form, and where beta is not 0. Because if beta is 0, this becomes a real number, and we are considering the case where you truly have complex numbers. Now, in this case, you will have two corresponding eigenvectors, and they will also be complex conjugate. If we denote them to be v1 and v2, these are vector valued complex numbers, and then v1 is the complex conjugate of v2, where this bar here is to indicate it's a conjugate. Okay, meaning that these two vectors will have the same real part, which is a vector, and their imaginary part will just have an opposite sign, which is also a vector. Formally, from our previous videos, we know that if you have find a eigenvalue and a corresponding eigenvector, then you can form a solution. So now we can form two solutions. Let's call it z1 and z2, where z1 we use lambda 1 and v1, and then z2 we will be using lambda 2 and v2. And then we know that these are both solutions. However, we know that lambda 1 and lambda 2 are complex valued, and v1 and v2 are complex valued. Therefore, these two solutions are both complex valued. And the solution z1 and z2 would also be complex conjugate of each other. And then in real-life physical models, we would want to have real-valued solutions. So we can do manipulation here to obtain those solutions using the principle of superposition. So we know that z1 and z2 are both solutions, complex, and the conjugate pair. And then by the principle of superposition, any linear combination of z1 and z2 will also be a solution. Okay, so let's manipulate them so that in the end we get real valued function. So let's take z1 and z2 and we do z1 plus z2. Since this is a conjugate pair, the imaginary part carries opposite sign, so what you get is 2 times the real part, and then multiply by half, you will just get the real part of z1 or z2 because they are the same. And then we can do a different superposition. That is, we look at the z1 minus z2, then the real part of them will cancel, and the imaginary part will add up, we'll get 2i. So then we can multiply it with 1 over 2i, and this will give us exactly the imaginary part of the solution, z1 or z2. So by the principle of superposition, y1 and y2 are both solutions, and now we see that these are real valued. Okay, so the conclusion would be, if a complex valued function z is a solution, then the real part of it and the imaginary part of each of them separately, they each are also solutions. Okay, another step is to show that the two solutions are linearly independent. So here I just say one can show that they are linearly independent. You can check the Wronskian. So we'll skip the details of that calculation. And then now they are linearly independent, so we can use them to form a set of fundamental solutions. Okay, therefore, we can use y1 and y2 to form the general solution. It will be y1 times an arbitrary constant c1 plus y2 times an arbitrary constant c2. Okay, it might also be a good idea to recall that y1 is just the real part of c1 and then y2 is the imaginary part of c1. Now let's try to derive the formula for the general solution. Now let's denote our two eigenvalues, and they are lambda and lambda conjugate. And we have two eigenvectors, v and v conjugate. So let's write it. Lambda now is just alpha plus I beta. I and alpha is the real part and beta is the imaginary part. And then v is Vr plus I Vi. So Vr is the real part of the eigenvector and Vi is the imaginary part. Okay, so let's write out one solution and just using lambda and v. And so formally this solution, let's call it z, would be e to the lambda t times v. And let's plug in. So we'll have e to the lambda, which is alpha plus I beta, t times v, which is a complex value, a vector valued function. So it's v, the real part, plus I times v, imaginary part. And now we apply the Euler's formula for the exponential function of a pure imaginary number. So the real part alpha times t becomes e to the alpha t, and then you have e to the alpha beta t. For that, you use the Euler formula and write it to be cosine beta t plus I times sine beta t. Okay, so this here is e to the power I beta t. And then the eigenvector is repeated here. So we see that this is a vector, and then what's in front here is a number. So it's a complex number, and this is a complex vector. Okay, so now we can distribute and write it out. So we can distribute this product and write out and collect the real part and the imaginary part of it. So we see the real part will consist of two terms. One is this cosine beta t times Vr, and the other is this sine beta t times Vi, because I times I is -1, and therefore we have a negative sign here. And then the imaginary part will also consist of two terms. One is this times that, we'll have I in the front, and then the second is this one times that, which will have an I in the front. So we put the I out and put the exponential function out and collect those two terms. Okay, so now we have found a complex valued function which is a solution to our problem. And we can use the observation we made on the previous slide to form the general solution. Because now we know the real part of it is a solution and the imaginary part of it is a solution, and these two solutions are linearly independent of each other. Okay, and then we form the general solution. The real part multiplied by a constant c1 and the imaginary part times c2. Notice that we only take the imaginary part, we don't take the I here, because we want a real valued solution. Okay, so now this is the general solution, and this is the formula of it. Okay, so I agree that this is not the most friendly formula to memorize. It would be easier to remember it in this form, and then just quickly work it out, and then you will get those. It's much nicer. Okay, just a comment. Okay, but now since we have derived this formula, we're going to use it to solve examples of problems. Okay, let's first consider an example with pure imaginary eigenvalues. Okay, so I already gave away. Okay, here's the example. Find the general solutions and sketch the phase portrait of this following system. X prime is AX, A is 0, -4, 1, 0. Okay, so the first step is to find the eigenvalues. This we shall be familiar by now. So the determinant of that, a minus lambda I, give us lambda squared plus 4, because lambda 1/4, and equals 0. And solving that, you see you get lambda squared equal -4. Therefore, two solutions are pure imaginary, plus minus 2i. Now, the second step is to find the eigenvectors. So we just need to find one of them, because the other one will be a complex conjugate. So let's just consider the lambda equals 2i and find the eigenvector of it. Okay, so this is found by solving this equation, a minus lambda identity times v equals 0. So putting the number, so we'll get this matrix here. That's the a minus 2i on the diagonal times v, which we say is a and b, equals 0. And then we know that using either one of these vectors times ab equals 0 will find it, because you see that these two vectors are scalar multiples of each other. If you multiply this vector by -2i, you will get this one. Okay, so let's use this one with a smaller number. We'll get a minus 2ib equals 0. Then we have a free choice. We can choose b to be 1, and then we'll have a is 2i. Okay, and then we can write out our eigenvector, which will be 2i here and 1 as the second entry. And now, since the formula uses the real part and the imaginary part, and let's split this vector into those two parts. It will be the real part and the imaginary part, and we just take each entry at a time. So the first entry is 2i, the real part is 0, the imaginary part is 2i. The second number is 1, and the real part is 1, and the imaginary part is 0. Therefore, we get this vector as the real part of the eigenvector, and this is the imaginary part. Okay, so let's pretend that we memorized that formula, and then we just plug it in. Okay, since the real part of the eigenvalue is 0, then we don't have the exponential function. Then you have e to the power 0, which is 1, and then this is the beta equals 2, the imaginary part. So you get cosine 2t sine 2t here, and that's the real part of the eigenvector, and here's the imaginary part of the eigenvector. Okay, and it is also nice maybe to write out the components, because the x vector contains x1 and x2, and let's write out. So x1 is the first entrance, then you will just take the first entrance of this vector 0, 2, 0, 2, and then multiply it on the scalars and add up. Therefore, the cosine 2t is gone. You just get sine 2t times 2, which is that one, and 2 times cosine 2t, which is that one. And do the same thing for the x2, the second one. You just go through, and then you pick this one, and then you go through, it's 0, and then here you multiply by 1, and here multiply by 0, and you collect it, and that's what you have. Okay, so maybe it's worthwhile to take a look at this solution here. What do we have here? We see that both x1 and x2 are just sine cosine functions, some multiplied by some constants, and all the sine cosine functions, they have the same frequency, 2t to t. So we see that they are both periodic functions with the same period. Now, next step is to understand how to draw the face portrait. Okay, so first we observe that the solution is a periodic function. And in fact, it consists of only sine and cosine function, and this is also called a harmonic oscillation. Okay, so after a period, the solution would repeat itself. That means the trajectory would go away and come back to the same point, and then repeat that pattern again and again. So therefore, all trajectories are closed curves around the origin. And second observation one can make is that all these trajectories should not intersect with each other. This comes from the uniqueness of the solution. Since the solutions are unique, then from the same point, there can only be one solution passing through. The third one, okay, this might be a bit witchcraft. I claim that they are actually ellipses for this problem, because if you take the expression for x1 and x2 as we have written them out in the component, and you do this calculation, x1 over 2 square plus x2 square, and you find out that it equals to some constant, which involves c1 and c2, but they're constants. And then this is an equation of an ellipse. And for different constants, you get different ellipses. Okay, so now we know that the solutions are ellipses around the origin, and what remains to determine is the direction. How shall we put the arrows around it? Okay, so let me get a color, red color. Let me say we have a ellipse here, just symbolically, and this is x1 and this is x2, and let me draw an ellipse, very bad ellipse. Okay, pretend this is an ellipse. So how shall we draw the arrow? So as time grows, how should be the solution go? Should it go this way, counterclockwise, or should the solution go this way, clockwise? How do we determine? Well, all one needs to do is just to pick a point on the ellipse and check in which direction the solution evolves. So let's take a convenient point, 1, 0, and try to figure out. So this is a point along the x1 axis. So let's say that is the point 1, 0. And then we can use the differential equation. So x prime, so how does the solution change at that point, is equal to A times x, right? So the A matrix we have, the x vector is now 1, 0. Do the product, carry out this product, and you get 0, 1. It's a vector pointing in the direction that the solution moves as time grows. So this is a direction 0, 1, which means it's pointing upwards in the y direction. So let me put an arrow in blue, so it's going upwards. Okay? And that is enough information. And because we know that if it starts to move in this direction and then it's a closed circle, it will just keep circulating in this direction. And all the other curves of ellipses will have to circulate in the same way. So we conclude that the arrows are counterclockwise. Okay, so let's summarize and put the plot them nicely. So this is plotted, and we have x1 and x2, and then all these ellipses we have here, and they're all pointing counterclockwise. You can add more arrows, but one is enough to indicate that. So we see that if you have a solution, it will go around the origin indefinitely as time grows. It doesn't go away, blow up into a bigger circle. It doesn't shrink, get smaller and smaller, and approach the origin. So the origin, if you start there, you don't move, because that's a critical point, which is an equilibrium. Okay, so all solutions nearby stays nearby. Okay, so let's give the definition of this type of critical points where you have pure imaginary eigenvalues. So this type of origin is called a center. As you can see, the critical point is right there. It's the center of all these closed curves which goes around it. Now, about the stability of a center, it's a bit different from nodes or saddle point, because there you have this so-called asymptotically stable, that is, as time goes, all nearby solution will approach that critical point. Okay, here the center doesn't do that, but it also does not have solution that will blow up and go to infinity. Okay, so in that sense, the center is called a stable critical point. We do not call it asymptotically stable. Okay, so you say it's stable. Why? Because solution don't blow up. But is not asymptotically stable because solution do not approach the origin as time goes.